just going to talk for half a minute and I'll hand over to Emil, who's going to start with an introduction of what Docker is and what it's good for. We have quite a packed evening. We're going to have 4 short talks. We're going to do them back to back. We'll start with Emil, and then we have Alex from Red Hat, working on Red Hat and Fedora. Then I will talk what we do within Transmode with Docker, and then last piece will be, where is it? Lasse on Spotify. Just one thing I want to say. That meetup here actually started out a little bit different than usually. There was Mario, is he somewhere? Here! Mario started the whole meetup actually, just with the question, is anybody using Docker and do you have anything to say? And then just an avalanche of comments, yeah, let's do a meetup, we want to hear more. And thanks for the initiative.
Yeah, so many people are interested. I just didn't want to do all the research myself, so it works out nice. I'll do it for you.
Yeah, thanks. So, Emil?
Right. So, great. It's great to see that there's so many people here. This new technology. How many people actually use Docker in production yet in here? No one. How many people? What's that?
Uses it outside of production.
Right? Who's even played with it? Who's tried firing up an instance? All right, that's good. Nice to see. All right. Well, the goal of my talk, I want to explain just what the problem is. What does Docker solve? Because it's a bit of a hard technology to wrap your head around to see what is it useful for, how is it different from virtualization, what does it do really? So I'm going to talk a little bit about some background to build this up, because it's really not so easy to see. Some call it that it's a lightweight virtualization tool, which is a bit misleading, because if you walk into it with that mindset, and it's pretty common, then you get very confused. When you see that you can only start a process, and then when that process dies, that your container is gone. So we'll get a little bit into that. And I want to push for the 2 things that Docker does, which is containment and reproducibility. That is to do something, and then you can do the exact same thing again. You don't have to be afraid of side effects that whatever someone else did on your server has changed, because you get this reproducibility through a container containment. So some things have changed recently in the past few years, and this is, I think, a great picture of it. Is that a few decades ago, client apps, apps were basically thick on the client side, and on the server you had a very well-defined stack that everyone used Apache to serve their web pages, and you didn't have these different layers in between. Maybe you had a cache proxy in front of it, and you ran some CGI scripts, or even served as static pages. And the thing that's happened is that we have gone from that monolithic architecture where you could assume what everyone was using, and then you can assume that you can deploy site A, B, and C, and D on the same server, and they would coexist because they use the same technology. But that is not the case anymore, because you have so many different application frameworks. You have the whole Ruby community, the Python community, if you do Java, and you have all these middlewares in between. That everyone has their opinion on which one is the best, and then this is the way it's supposed to be, and I expect this server to be running, and so on. And this means that it's become so much harder to provision our servers. And also, the second thing that's changed is that computing power has become a commodity. Back in the day, we used to set up a server, and that was like a big thing. We bought the physical hardware, we configured it, and then it ran for its lifetime, and then it shut down. Today, we can spawn instances on EC2 in a matter of just for a day, because we need it. And we fire up, we want to scale out our applications, we fire up new instances of our app, just like that, and we take them down again. And this means that for every service, every one of these little services that makes up your app has to work in every one of these environments. Because you have your local environment, you have all these things. And this gives rise to the matrix from hell. To make all of this work, deploying an app, it's not just pushing your code. You have to make sure that each one of these services work on every one of your environments. So I'm a programmer, and that's what I do most of the time. And there are some things that I've learned that help make my life a lot easier. Those things are avoiding globals, separation of concerns, and to be explicit about dependencies. And these things, I think it's hard to do in system administration. Most people use some provisioning tool like Puppet or Chef to manage this. But still, there are so many components, there are so many things that you expect to happen to be in place that the knowledge of these things is in your head instead. It's inside the head of a certain number of people who work with the systems. And I think a computer could do that much better, because that's what computers are for, keeping track of tedious things. The goal of these things is state and determinism. This is a little abstract, but basically if you know where you are, and you have a deterministic function that does something, this is a bit of functional programming, you know that what's going to happen later, the state you're going to be in. And that's programming, and in the SysOp world, this translates to containment and reproducibility. So you see, containment is that you know your state, you know what you got, it's not going to change. If you fire it up once, it's going to work again. If you fire it up again. So that's reproducibility. So right now, provisioning, it usually looks something like this. You define your server state, as a check, but then you run it on a dirty server. Unless you do the Netflix approach where you spawn a new AMI, a new server for each, every time you're going to do a deployment, you spawn a whole new server. And that takes a long time for it to start up. You're starting the whole OS with everything that it has. It takes minutes to start just to do the same thing. And then you run your app, and then when you deploy again, you shut it down, and it's all dead, you do it all over. So what's happened then is actually that the OS has just become your app. And the hypervisor that EC2 is running, or whatever, if you use your own hypervisor virtualization, has become the OS, because you start servers like apps instead. And I don't know if it's something people recognize, that this is what you sort of do after a while. Because the other option is to just write your provisioning scripts and then just run them and hope that the same thing happens again. So the basic problem is that you don't know what state your server is when you start. And there is a reason for this, that this is the way it works. Unix that I think most people here are using, some Linux or something like it, it was designed when people logged in to your servers with shell access and they ran binaries. And so it made sense that, I just installed the latest send-mail version, just so you know. So like everyone who's on the same server, they go and log in and they update their apps and so on. But right now, it doesn't work like that. Usually you run a few apps side by side on your server. Or maybe you just run one of them. And you just want your app to work. You don't think so much when doing an upgrade of all the packages on the system. You just want it to work. So that's why we need to change, I think, how you run and distribute our applications. And the key to that, I think, is to ship software as a whole. Because right now, when we ship your software, you have your application, you have your dependencies, your configuration, you need maybe a certain kernel version, some modules, and so on. And all these things you got to run. It's not just your code. And right now, there isn't many ways to do this unless you're really clever. And that's what .cloud is doing. They were making it themselves. .cloud is the company that created Docker. Because they saw that the only way you can do this is to wrap things up in one container. And deploying an app, sometimes it can feel like this. You have all these spread boxes and things that you want to put together, and then usually something goes wrong, so you try to do it a few times. And that's why, in the shipping industry, physically, people came up with this thing, shipping container. It's so much easier to wrap your head around. Rather than have to deal with all of this, you just have that. And no matter what's inside it, it will fit in the same space, you can use the same tools to carry it, and the person who carries it doesn't even need to know what's inside of it. And that's really profound. I think this is an amazing picture. This is one of EC2's containers, a computing container. So this is what it looks like. They can deploy one of these wherever there is electricity and and network connectivity. And what's even more amazing, I think, is that one of your apps could be running inside of this container. And the people that manage it don't have to know whatever those apps are. They just provide the infrastructure, and then you put your pieces in. And your pieces happen to be virtual service, AMIs, images. But so it's a complete separation of concern. The person who puts the container in place doesn't need to know what's happening inside it. And right now, there isn't really anything like that for software, except for Docker. Where, I mean, there are other alternatives, but they're not being used. In Docker, that's why you really need to push for it. So basically, what we would need is a container application and its dependencies. They were transferable, so we can put them anywhere. They ran in isolation from everything else. It doesn't matter if you run 3 web servers of the same kind, if you run 3 Nginx instances on one computer, they should have nothing to do with each other. You shouldn't have to think that, oh, I got this running already. And of course, they ran everywhere. It doesn't matter if you run it on your laptop, in a virtual environment, or if on an EC2 server, or on a bare metal server in your closet. It should work the same. And this is the key. Because up until now, we have ran virtual servers with this to achieve this. And they're heavyweight. They take minutes to spawn, and we do so much that it's unnecessary. We waste cycles, we waste memory, we waste time on this. So, right, I'm going to do some hands-on sessions with Docker, because I think that's a good way to wrap your head around it. And of course, I won't have time to cover everything that it is, so I'll just show a little bit of the basic, how it works. Alright, can everybody see in the back? So first of all, I'm running Mac OS 10. So I need to Docker only runs in Linux currently. The goal is to have it run just about anywhere, but right now it just runs in Linux because it uses something called LXC to do its lifting. So how many ever use Vagrant? Right? Awesome. Okay, so Docker just since you need read privileges to run Docker client. Okay, so first of all, you need an image. Docker still has images, and they're sort of like virtual machines. So I already got some images pulled down just in case there was a network here. But how it works is basically you can do Docker pull and then a repository. What it's doing right now is that it's actually pulling a file system. And it's not that big, because the key with Docker is that you don't need so much. You just need the basic environment to run your program. That is some libraries and some binaries like ls and libc and so on. So doing a lot of stuff. Alright, so we have these layers. So the simplest thing you can do, of course, is to SSH into your computer. That's the first thing you do if you try this virtualization tool. The equivalent here is that we usually start an Ubuntu image, and we gotta specify what we want to run. So in this case, I'll just spawn a shell. So there it is. Right now, what happened right now is that we created a whole new process group. We created a copy of a file system, where actually we didn't copy anything, but it's because it's copy on write. So we have a complete clean slate, and it took that quickly. So this is the equivalent of spawning a virtual machine in Docker world. It takes in the order of milliseconds. So that's a big change. Another cool thing to notice is, of course, everything is scoped. You know, the init process, it has the pin 1. Well, if we look outside of the machine, you can see right here. The process here, this is from the view of the host that's running the real kernel. And on the left side, we're running inside a container. If we do spawn some processes like this. So now we get a tree. So what we see here is that these processes are spawn inside here. But from the perspective inside the container, you see the pits are different. So there's no way, unless you're a really clever hacker, to break out of this shell, this jail. And it's a lot more than a jail. It's on the it's in the kernel level. The processes have their own namespaces. And of course, we can do whatever we want inside here. We can even do something fatal. We can remove everything. So right now, I don't have a file system. Nothing but we'll see if it works. Bash. So let's see if we do this. Alright, so now I'm back outside of the container. I exited it, and the thing that's happened now is that we no longer have anything running. Because it's not like our machine is running. Because the process that was our machine has quit. We quit it. That was bash, shell. However, we can still see that the container will be safe, the file system. So what we can do is we do a diff. Let's see what happens. See that we deleted everything inside the container. And imagine the power of this is that whatever you do inside the container, you install a package, you compile a web server, and install it, is that you get a specific list of everything that has happened. So everything is contained. And that is really powerful. There are many implications of that. So this case is kind of pointless because you can start a shell. I mean, you can use the system. You can use that for things too. More interesting is that you can spawn background processes with Docker as well. And you see when I ran the previous command, I said -t -i means give me an interactive TTI, a terminal, basically. So what we can do instead is, if we say here, we say -d, bam. So nothing started, of course, it just quit, got nothing to do. So what we can do instead is we write a really simple, this is like the mother of all demos for Docker. So we write a super simple inside of it. Let's see if I can get it right.
Do right now before it.
Oh, right. Thanks. There we go. So now we get something running. See, it's running. So how can we do anything with it? Well, we can attach to it. Attach, in this case, it means to like pretend that I had started this in a terminal, attach to the TTI and see what's coming out of it. So, see how we, oops. So you see this little IE here. This has sort of the same semantic as git shots, which is pretty useful. You can just write the first view. So alright. So what happened here is that we see something. So this is running in the background. So the idea here is that you can make your apps and you start them just like I did this simple daemon here, and you can create Docker files and so on, which I think will be covered later by Matthias and maybe Alex. That basically do elaborate examples where you can just do like Docker run Nginx, for example. And I'll actually show you a little bit of that. How are we doing time-wise? So I prepared a small example using something called a Docker file. The thing is, this Ubuntu image here that we had, it was created by basically installing Ubuntu in a CF root jail and then creating a tarball of its file system. You remove everything you don't need. So a useful thing would be if we know that we got that get, for example. This is a Docker file, and it's a pretty simple language. It's actually similar to Provisioner, like Puppet or Chef, except that it's just work with Docker and lets you run commands inside a container, and then it saves the result as an image. So we say here that you start with an Ubuntu image, and then we do a bunch of stuff, which in this case is to install the necessary dependencies. And I think this is where Docker shines, is that this you would specify in a manifest in Puppet or Chef. Even for the most simplest thing, you would have to exactly specify what you need, like dependencies in between them because it's declarative and not imperative. But for just a simple example that you can do on the server, you know how to type the commands to get it running, you can put it in the Docker file, and it's a decent way of creating a containerized software that you can deploy and send to someone and say, hey, this works, it's just a box, open it. So what we do, we add files. This is another important thing that comes a bit unintuitive, which is that the file system in Docker is frozen. I mean, whatever is in there when you start the container should stay there. You shouldn't expose things so that you have outside things that can change. You should make sure to contain everything so it's always the same whenever it starts. And so the way to add things is here using this add command, and it says specifically add this file. So now you know that you changed something. It's not that you log into it and magically edit it and then forget about it and save it and hope that someone else remembers this. It's actually specified here. So we do that is we run the bash and build it. It's a super simple script. That. And then we add some folders, we add some configuration. So what this thing is doing is configuring and compiling Nginx. And then comes this sort of magical thing. We expose the port 80. And we say here that this is the command to run when the file is, when the container is run. Automatically, we can just do docker run Nginx later on, and it will do this thing. So we can do that.
Could you please run the commands higher up on the screen? Hard to read.
Right, absolutely. All right. So I got my own Nginx build. And now you may wonder, why would I want to build my own Nginx in the package system? Well, that's the point, is that the package system will change, and most people they work around the package system to make sure their app is consistently running. Because there's so many things that could change. We could have a specially compiled version of ImageMagick if we want to transform images that has these flags and so on. So right now, we should be able to start this container. If we do use the images, we see that now we have this Nginx image here. So we're going to run in the background, it's a web server. Now we have web server up. See here, it's running along with the daemon here. Docker lets you kill processes as well, of course. Right? The important thing here, and this is something that most people stumble upon and really hit hard when they start working with Docker, is this port mapping you see here. This means that the port number 49155 is mapped to port 80 inside the container. And this is, if it said that it mapped to 80, if you map so that you start a web server on port 80, that would mean that you cannot start as many containers as you want. The cool thing here is that I can run this as many times as I want. You see, I've got 3 Nginx servers running now with the same configuration on the same server without thinking about it, without thinking about anything that they will mess with each other, that there will be conflicts because I have the same thing running. So the problem instead becomes how to expose this. Well, most people use some load balancer or HA proxy or something to redirect the traffic. So we can try this. So I set up the bigger machine to have the 1, 2, 3, 4 IP. Right, so that happened inside. That was the container that ran. Serve the file. And the cool thing now is, let's say that you see, I added some configs and some Docker roots here. So go into Docker roots. Actually, you know what? I don't have so much time, so we'll just do we can break out of this thing, because this is the question you had before, which is that can you expose files outside of the container somehow? So that, because now everything, even our log files are inside the container, and those are obviously interesting for us to see. So what you can do then is that you can say that you want one path inside the container to be mapped to an outside point in your file system. So let's say that I want to map current directory to /document inside the container. So what's happening now is that I have one point inside the container now where I can change things from the outside while it's still running. So we can try this. So now nothing changed. However, that first container didn't change because there was no mapping to the outside, so it's completely frozen. And I think this is really the great thing, is that you specify what you want to expose. Everything else is isolated by default. So that's pretty much what I wanted to show with Docker, and there will be more. I don't know, do you have any questions, by the way? Is there anything that's unclear? Crystal? Alright.
Got one question. How do you transfer your Docker files?
Right.
I mean, from developers to production.
Right. Okay, Matthias will take that.
Okay,
There's
great.
this great thing called a registry that he'll talk about.
All right.